Yeah, so thank you, Sakuntala, Kavita, and Tridib for organizing this. So today I'm going to be talking about the effect of a particular dynamical feature, that is of a non-local hops, on the totally asymmetric exclusion process, and various problems within the totally asymmetric exclusion process. So this work has a connection with Mustansir's work.
Um,
Uh,
could you
at the
please
work,
switch on your video, please, Apoorva?
I already have. Sorry,
Oh, we can't
just a
see
second.
you.
Just yeah. So this is connected to some earlier work by Mustansir, which is the chipping diffusion aggregation model, where essentially you have the dynamics. So you are working in one dimension and with periodic boundary conditions. The dynamics are symmetric, and so basically what happens is you can have two kinds of moves. Either the whole cluster can move to the next site, one of the two nearest neighbor sites, and basically join together with all of them and form a new cluster, or one mass can chip off from a cluster and move in either of the two directions with equal probability. And here one sees a phase transition. Depending on the density, you can have two phases. So one is a phase with an exponential decay of the mass distribution decays exponentially. And the second is an aggregate phase where, apart from a power law decay of seen at lower masses, you have the formation of an infinite mass aggregate. So this was done by mean field theory numerics, but also later it was shown uh, exactly in arbitrary spatial dimensions. And this here is the condition for the phase transition. Further, it was seen that asymmetry in dynamics, so the particles trying to move favorably in one direction, has a significant effect on the phase transition, in that if there is asymmetry, the phase transition is no longer there, and so there is no aggregate phase in one dimension when there is a bias or when there is asymmetry. And so what we will show in connection with this work is that if there is an asymmetric motion in this model, in the CDA model, but there is one slow site in the model, and we'll define what a slow site is. Then again we start seeing a phase transition between an aggregate and a non-aggregate phase, and we have derived the condition for that. Okay. So coming to what we did, so this is some work that I did with Dr. Kartika when she was at IST doing her PhD, and so this is where it is published. And so I'll talk about generally the dynamics to begin with, and then on its effect on the asymmetric exclusion process with open boundaries, as well as with periodic boundaries, but in this case with two kinds of defects, dynamic and static defect, and the connection to the CDA model. So the dynamics is simple. It is like the usual asymmetric exclusion process. There is hardcore exclusion. You cannot have more than two particles on a lattice. And So a randomly chosen particle can move, uh, can take either of the two steps. It can either move to the neighboring site, nearest neighbor site, with probability 1 minus p, or it can make a long or a non-local hop all the way to the unoccupied site before the next occupied site. So this is like driving your car very fast till it reaches the car in front, something like that. Uh, so this is the dynamics in general, and so we'll discuss specific cases. So motion is unidirectional, so it is a totally asymmetric version of the dynamics. And this kind of dynamics was first proposed in this paper by uh, Ha, Park, and Denise. Uh, so what we do is, in the version of the open boundaries, it's the dynamics was as described, but the boundaries come in as follows. So the particles can enter the left boundary with the rate alpha and leave the last site L with rate beta, as in the usual asymmetric process. But the very last particle cannot just directly hop out of the lattice in one single move. Rather, even if there is nothing on the last site, it will first, before entering the reservoir, it will come to the last site, and then from there it can move out with the rate beta. This effectively builds in the exit boundary as an important boundary in the system, and so one can explore the phase diagram in the three-dimensional space, and essentially, so we did numerics as well as mean field theory for this model, and what we see is that the system shows four phases. Three of them are the usual phases that one sees in the totally asymmetric exclusion process, namely the high density phase, where the input rate is higher than the output rate and the density in the bulk is controlled by the exit boundary. The low density phase, where the input rate is smaller and the density is controlled by the input rate. And the maximal current phase, where the bulk density is no longer dependent on the input or the output rate, once both of them are higher than a certain number. And and the current value in this whole phase is constant, and it is the maximal possible for a given system. And in this case, with the variation of P also, we see all these three phases. Of course, the current in the maximal current phase varies with P, but at least at a given P, it's the same throughout the phase. Apart from these four phases, one sees an additional phase which is called the empty road phase, and this happens at very low values of the input rate. Uh, and what happens here essentially is that particles enter on the input side, and as soon as they enter, because the value of P is high enough and they don't enter at a large enough rate, they can essentially very quickly make a long hop all the way to the exit side, and from there they get out. And so if in this state you see the density in the bulk, the density is essentially zero, because the particles are just skipping the whole bulk and going to the other side. So these are the sort of four possible phases in the system if you introduce this additional feature of non-local hops. And what one sees is that when you vary this parameter P, P equal to 0 is of course the usual asymmetric exclusion process, and we see that alpha C and beta C is 0.5. But when you increase P, you see that initially that there is on the low density size, it gets divided into two, and you get this additional empty road phase, while the maximal current phase slowly starts to become smaller and smaller. And finally, what happens in numerics, what we see is that for a given value of P, which is the probability of the non-local hop, um, uh, the maximal current as well as the low density phase, they both vanish, and at the same value of P. And essentially you only have two phases left in the system, which is the empty phase and the high density phase. And so our numerics show that this happens at P equal to zero point 0.3. And we also did mean field theory, which I'll try and show briefly, and where we see that it shows that these two should happen at very different values, but our numerics very much disagree with that. So the mean field theory was set up as follows. You essentially have two terms. So you take current through a given link, and you essentially have two terms, in terms of the density at a given site. So the first term is the usual tacet term, where you have a current due to the local hop, while the second term is the current due to the non-local hop. And what it requires is that if there is a given link, there should at least be a particle before the link so that it can cross the link. So you should have the probability of that, and then of course the whole passage should be free. So at least the site just before the link should be unoccupied. And so this is the expression for that. And if we consider the bulk, we can consider that there will always be a particle somewhere which can cross this link. So we do not have this term of ensuring that there is a particle. And so again, you can do the analysis here, and you
We
see.
have 2 more minutes.
Okay, fine. So yeah. So basically, you can determine the various phases from here, And yeah, these are the this is the J versus rho curve as compared with numerics and the mean field theory. And the agreement we see works better in the high density phase, where the dominant boundary is the exit boundary, and the long hops they seem to introduce correlations, and the mean field theory no longer doesn't work very well. Okay, so in the limit time I have, I would like to discuss this other thing which is connected to the model that I described at the beginning. So we consider the same model of local and non-local hops on a periodic lattice this time, and with the additional thing that there is one slow particle which I show here with the hexagon. uh, this slow particle is slow in the sense that it can only make a local move, and with some rate mu. Okay. uh, and so what we see in this case is that again there is a phase transition, and between two phases. One is the homogeneous phase, where there is a constant density across the lattice. There is a little phase, a boundary region close to the slow particle. But then at large enough p or small values of mu, with basically very slow particles, you see the formation of a shock. And so there is a macroscopic region of density zero that develops in front of the particle. So this is basically slower when the defect is either very slow or the density is very low. The this shock can form. And again, one can do a mean field theory here, building it on the speed of the particle, saying that the speed of the particle just behind the slow particle has to be the same as the slow particle. And from there one can derive the condition um, uh, for the phase transition that I just described. And so this is a sort of 2D surface in the 3D phase space of mu, rho, and p. And what we have done is we have taken slices of this, and we see these two phases. And so the dots and dashes are the numerical results, while the red line is the result from the mean field theory. And the connection to the CDA model is here. So basically there is a mapping that exists configuration to configuration between this and the CDA model, where essentially the sites translate to particles and the particles translate to sites. And therefore the move that I earlier described in the CDA model of the whole cluster moving is essentially equivalent to the long hops in our model. And the chipping move of a single particle moving away is that of a local hop. While the slow particle in our case becomes a slow site, and the slow site is as follows: that out of the slow site you cannot have the movement of the whole cluster. You can only have a chipping move, and with some rate mu. And so remember that if there is no disorder site, or if there is no slow site, there is no transition in the CDA model in the presence of asymmetric dynamics. But once you introduce that, you get the phase transition to a state that has an infinite aggregate, which is basically the shock phase, the big shock in our model. So the big empty portion translates to the big cluster, that is the infinite cluster in this model. Uh, yeah, so that is the connection, and then you can translate into the language of the CDA model, where you have so rho d is the density in the CDA case, and this W is the parameter, which is the ratio of the two rates of non-local and local hops. So I do not have much more time, but just let me
I
describe the.
think we have crossed like over by 2 minutes.
Okay, so just one more result about
Mm.
a static defect which we considered,
Um,
where again we see a phase transition, and we compared our uh, you know the uh, uh, the numerics as well as the mean field theory, and they agree well in this case. And here the transition, there is always a formation of a high and a low density region. The phase transition here is between phases where one side is has a density zero, versus one side having a density finite density on one side. So that's all I want to say, and with that I'll stop. And
Okay. Thanks for the nice talk. We can take some questions now. So I don't see any raised hands.
I had one question.
Yeah, Deepak, please.
So you said that there is a long range interaction and hence the mean field theory doesn't work. But I thought if the interaction is long range, then the mean field theory is better.
So the fact that I mean the not the long range interaction, that I mean there is a correlation in density at one side and the other side. So
Okay.
I mean one assumes that the neighboring sites are uncorrelated and so on. So
Okay.
that yeah.
Okay. Yeah, Mustansir, please.
Yeah, Apur, your final phase where you have, slowed down and empty road in front, is that like the Janowski-Lebowitz thing with a single bond and a single slow site?
This one static defect.
Yeah, right.
Yes. So the originally, yeah, I mean, so it is the same model, but with the inclusion of a of this long
Long
Hauff
range.
dynamics,
I see.
where essentially again the long dynamics is such that wherever there is a static defect, you cannot cross the site with the static defect. So it
Right.
has this effect, and you have to land there and then move.
Okay. Yes.
If not, let's thank the speaker once again. And